Okay. Assalamu alaikum, dear students. I'm sorry for sending this very late, but I was just trying to recover from my cold, and alhamdulillah, I'm much better now. That's why I decided to wait this late before doing it. So we'll try to inshallah finish chapter 7 today, and so very quickly we have talked about enzyme specificity, and we have talked about the different uh, proteases like chymotrypsin and trypsin, how they work. So let me just so we've talked about chymotrypsin, and we've talked about trypsin and the specificity for these two guys based on what is there before for the carboxyl group coming in, right? Okay. I've also sent you mechanism about the slide and video about how chymotrypsin works, and essentially trypsin works the same way as well. They are all serine proteases, and again we've talked about this as well, this slide. And here's a mechanism of action. Again, I've sent this to you already. You can just look at that. You can see this link here. Right? Okay. Now, moving on, this is new stuff. So when we talk about catalytic mechanism of how enzymes do what they do, we find that they actually use uh, two or three different mechanisms, right? So they basically use three mechanisms, um, uh, and actually they use more than three, but we'll talk about three. So the first one we'll talk about is what's called this general acid-base catalysis, right? In general acid-base catalysis, and we've seen this with chymotrypsin, where serine OH attacks it, but it doesn't attack unless histidine, right? So this is where histidine is. So histidine takes the protons. Histidine acts like a base and takes a hydrogen away from the serine hydroxyl group and makes it a very strong nucleophile, this O minus, and which attacks the partial positive carbon, and the reaction proceeds therefore. So this was an example of a base, which is histidine, taking a proton, right? And in fact, if you look at aspartate, which was before histidine, so aspartate acts like an acid and takes, um, you know, uh, takes the proton away. Sorry, it acts like a base, takes away the proton, and histidine acts like a base, takes away a proton from serine. Okay, so just know that one of the mechanism enzymes work by is to use what's called general acid-base catalysis, and this is based on donation or acceptance um, of protons, right? And we see this in this example. Okay, the other mechanism that enzymes use um, are called nucleophilic substitution reactions, right? And here again these are SN1, SN2 reactions. So you can see this is a nucleophile attacking a carbon center, and you form a bond and you actually break a bond here, right? So those things happen. So again, for the sake of time, I don't want to go in more detail. So the second way enzymes do catalysis is they use nucleophilic substitution reactions. The first one was acid-base catalysis. Okay, and you don't have to memorize the structure. Just know that it's SN1, SN2, and um, you know, the nucleophilic electron-rich atom attacks electron-deficient atoms, right? So this is what you have to keep in mind. Okay. The third way that enzymes do catalysis is what's called using Lewis acid-base reactions. If you remember from General Chemistry 1, acids are proton donors, and bases are proton acceptors, and they are what's called Bronsted. So it's called Bronsted acid, right? Um, and bases. So these are proton donors or acceptors, donors and acceptors. Okay. Um, so this is Bronsted acid bases, but you can also have Lewis acid and bases, and as shown here, this is Lewis acid and bases, and these are not working with protons, they are working with electrons. And just like acid is a proton donor, um, they could be electron acceptor. So this would be a Lewis acid, right? So Lewis acids can be proton donors or electron acceptors, just the opposite. Likewise, a Lewis base would be a proton electron donor. So it turns out a lot of these metal ions can work like Lewis acid, right? And as an example, there's an enzyme called carboxypeptidase, which is also a protease. It uses zinc in its active site, and zinc is essential. And if you look at the mechanism, so you have zinc here in the active site, and in the Zn2 plus state, right? And it is basically accepting a lone pair of electrons from oxygen, right? Um, and it pulls it such that it makes this carbon very electron deficient. Um, so you get this partial negative, partial, and so this is ready for an attack. So it basically activates the carbonyl for a nucleophilic substitution reaction, right? And this is shown again nicely here, where you have the zinc, and what is shown here, this is the substrate. So let me highlight the substrate. So this is all a substrate, right? So this is all in highlighted in yellow is the substrate and the active site of carboxypeptidase. This is the enzyme, right? It's a protease enzyme, but it uses zinc, and what zinc does, it acts like a Lewis acid. This is a Lewis acid, and it pulls electron, it accepts a lone pair of electrons from, so it's pulling them towards itself, right? And which activates this carbon for a nucleophilic attack by water. This is water attacking it. This is water attacking it, right? And the same thing is shown in the next this slide here. Exact same sort of thing is shown here, and also I think in this slide as well, right? That the zinc is pulling electrons from here, and water shown here. This water attacks the carbon here. Okay, so you don't have to do not memorize that the mechanisms. Don't do anything except to know that there are three mechanisms. One is general acid-base catalysis. Second one is nucleophilic substitution reaction, SN1, SN2 reactions, and the third is Lewis acid, Lewis base mechanisms. Okay. Um, Moving on very quickly, we know that enzymes show what's called stereospecificity, and we've talked about this a lot, that enzymes can only work on L substrate or the D substrate, and they're showing you if you have a chiral substrate, it'll only bind to the binding pocket such that specific atoms will fit in certain places, and that's where the specificity comes from, right? They show the enzymes are stereospecific. They only bind to the L or the L or D substrates and not otherwise. Now, and this is actually almost the end of chapter 7. So if you look at the enzyme-based reaction, um, we talked about how every reaction has to go through this hump, and we call this hump activation energy. Right, so this is the EA, activation energy. And what enzymes do, they lower the activation energy, right? And so enzymes lower the activation energy. And what is this point? This point is called TS, or the transition state. And if you ask what is a transition state, what people say that the transition state is basically a chemical species that is intermediate between a substrate and the product, right? And what that means is it is neither, it's somewhere half substrate, half product. It is not the full product. Product is here, substrates are here. It is in between the two of them, right? And in fact, this is shown here. So um, if you have, for example, a substrate which is, C chloromethane, this guy here, right? And OH is gonna attack it. This is the SN1, SN2 reaction, right? And what's gonna happen is, you lose the chloride, and you'll get OH added here, right? Okay, so this guy is a product, right? So this is the product and this is the reactant. Now what is the transition state in between the thing? And they're showing you the transition state would be you'll see the chloride losing, and you'll see the hydroxy group being added, right? So you have a bond being broken and bond being formed. And that's called the transition state. Now what enzymes do, one of the ways that enzyme catalysis proceeds is enzymes stabilize the transition state. They make the transition state, they make this guy very stable, right? So in the active site, there's a space where uh, uh, there are side chain of amino acids such that the transition state, when it's produced, is stabilized by electrostatics, by charge interaction, or maybe hydrogen bonding as well, and keeps them very happy, and it stabilizes it so it comes down. So the energy of the transition state comes down, and that's how enzymes can catalyze. Last thing that remains is actually two points. One is called the concept of coenzymes. So it turns out that oftentimes um, there are enzymes that we call them apoenzymes. So apoenzymes are only the protein part, right? So it turns out if you have a protein-based enzyme, just the protein, amino acids, and so on and so forth, it is not active. It needs a helper, and then the helper is called coenzyme. So this is a helper, coenzyme, and coenzyme will bind. So coenzymes are non-protein parts, right? And I'll explain to you what these non-proteins. They could be amino acid. They could be organic molecules, or they could be metal ions. And when they bind, the coenzyme binds to the enzyme, they become an active enzyme. We call them holoenzyme. So apo is just the protein part. Coenzyme is the non-protein part. Together they become holo, which is the active enzyme, and then they can bind to the substrate and carry out catalysis. So not all enzymes need coenzymes, but a lot of them need coenzymes. So if there's any enzyme that needs coenzyme, that enzyme is made up of apoenzyme and a coenzyme. Okay, so um, so this coenzyme, again, we said they are non-protein parts, and they could be metal ions or they could be organic compounds. So metal ions like zinc and copper and iron and so on and so forth, this would be metal ions. Or organic are things that are made from vitamins, and we'll see this. So for example, you have a lot of these vitamins like vitamin, like biotin, or vitamin like B6 or niacin, which is B3, right? B12 and so on and so forth. These, like niacin, for example, niacin is used to make what's called nicotinamide adenine coenzyme, or NAD. So if you hear the word NAD or NADH or NAD, it's coming from the vitamin niacin. And what NAD plus or NAD or NADH, they're involved in oxidation reduction reactions, right? So I want you to know just uh, two examples here, please. Just know two examples, right? So you can say, for example, um, riboflavin, for example, which makes flavin coenzymes. You can look at niacin that makes NAD plus. Any two enzymes, any two examples. So of vitamins and coenzymes, the vitamins that make the coenzymes, and the reactions they carry out, and the reactions like oxidation reduction reactions and so on and so forth. Okay, just memorize that, please. Okay, this is a structure of NADH or NADH. As I told you, it comes from niacin, but do not memorize the structure of this. But know that it is used in redox reaction. It's used in oxidation reduction reactions, but do not memorize the reactions. Okay. Just again something. Just don't worry. There's no time. We'll move on. Okay. Just move on from there as well. Okay. The very last part I want to talk about in 2 minutes is the concept of ribozymes. And again, ribozymes are non-protein enzymes, right? So we talk about this in the beginning of the class, that there are some enzymes that are not made out of proteins or amino acids. These are made out of RNA, RNA enzymes, and we call them ribozymes. There are a bunch of them. Don't worry about all those things. There's just a lot of detail. I don't want you to memorize anything, but just know that you can have RNA-based enzymes, and none of this is important. Don't worry about this, right? Okay. So and this is not important. Don't memorize it, right? But just to know what was happening here is you have this guy, and I'll highlight in green. So this is enzyme. It's RNA-based molecule. It binds to this guy, which is a substrate. So this is my substrate. So it binds to a substrate, right? So enzyme binds to a substrate, and there's hydrogen bonding going on, and an enzyme cuts it. The enzyme causes it to be cut. There's just like peptide bond being broken, and it cuts it, and you have two pieces, one product and two product. I'll highlight in yellow. This is one product, and this is the other product, and then the enzyme is still exactly there. So the enzyme it takes part in the reaction but doesn't get used up. And what you have done, you have taken this substrate and you've broken them down. This is a substrate and yellow, and you've broken it down into two parts like this, right? So that's all I'm showing you. So don't memorize this. Just know that this is what enzymes, RNA-based enzymes work just as nicely as protein-based enzymes. So again, just don't worry about this as well. And just to let you know that in the ribosome, right, where proteins are made, you have amino acids coming in, and they become polypeptide, and this happens in the ribosome, and inside the ribosome, and there's an enzyme that joins two amino acids together, right? And it turns out that that enzyme, which is again which is called peptidyltransferase, it joins two amino acids together, right? Uh, Again, don't worry about the mechanism, but that enzyme inside the ribosome, um, which is called this peptidyltransferase activity in the ribosome, that enzyme turns out to be an RNA-based enzyme. So RNA-based enzymes are very, very important. They are found in the in the uh, in the ribosome, and in many other places. So they really are very important. It's not that it's not important. They're critical for life, right? And a Nobel Prize was given for this discovery. This is Tom Cech and this is Tom Stites. These two guys, they got the Nobel Prize in 1989, 1990, right, for this discovery of discovering RNA-based enzyme. Okay, so this is the end of the chapter 7 for us, and I think I took 25 minutes, and we'll go over this tomorrow, inshallah, in the class. Sorry for that bad video. I'm sitting in my room and the lighting is not the best, but inshallah, I hope you were able to hear me and follow through the slides. All right, take care. We'll see you tomorrow. Assalamu alaikum.